I today will start with a correction. I told you I cannot remember names very well. So, here what I wrote as lower triangular matrix I was suspecting is called upper triangular matrix. If all the numbers below, all the entries below the diagonal is 0, we call it lower triangular. If all the entries above the whatever I call as the lower triangular matrix is called an upper triangular matrix. Upper triangular matrix, all the elements which are below the diagonal are 0. In the lower triangular matrix, all the elements above the diagonal are 0. Okay. So, I hope you pardon me and I make the corrections. So, today I go to the situation where I have defined what is A and the product between A and B, what are the requirements on the rows and columns, that the number of columns of A must equal the number of rows of B. Now, defining A B does not guarantee that I can define B A unless the number of columns of B matches the number of rows of A, because if B is an n cross k matrix and you want to form the product B A, then the number of columns of B, which is k, must equal the number of rows of A, which is m. So, this is a requirement. So, even if you have that k equal to m, so if you multiply A into B, when if k is equal to m, then you get an m cross m matrix. If you multiply B into A, you get an n cross n matrix. So, A B, even if you have A B is not obviously equal to B A, because the size changes. But if you even have a square matrix and you multiply A B and then you multiply B A, A B is not equal to B A. That's in general, but in some cases yes. As an side observation, which I learned when I was in the undergraduate, and I like this kind of observation, that any square matrix can be written as a sum of a symmetric matrix and a skew symmetric matrix. So, every matrix has a symmetric part and an asymmetric part, and it can be decomposed into those two parts. And this is very simple, because you know when A is symmetric, it means A transpose equal to A, when A is skew symmetric, it means A transpose equal to minus A, and it is a very simple algebra to prove that if I take A and B two matrices, add them and then take that transpose, it is same as taking A transpose of A first and then adding it with the transpose of B. So, it is just A plus B transpose equals A transpose plus B transpose, and then you can observe that A plus half, A can be written as half is just a scalar, here you are multiplying A plus A transpose plus half of A minus A transpose. So, it is a kind of very clever decomposition. A plus A transpose transpose, where you apply this formula, A plus B transpose is A transpose plus B transpose, A transpose plus A transpose transpose. A transpose transpose is again A, which is obvious, which I do not have to tell you, and which means I get again A transpose plus A, which is A plus A transpose. So, here I have symmetry. So, this is a symmetric part. Well, A minus A transpose is again A transpose minus, or you can have minus A transpose of transpose, which is same as A transpose of A transpose minus A, which is minus of A minus A transpose. So, you can say how do we handle the minus? We can handle the plus. So, instead of this, what you will write is what is minus of A transpose? It is plus of minus A transpose. So, it will anyway become minus A plus of minus A transpose transpose. So, that will similarly tell me that this is nothing but minus A. So, it will be minus of A minus A transpose. So, it is skew symmetric. Now, we will focus on a notion which is extremely important, and that is what we will be, in many cases we will be repeatedly needing, is the focus on the notion of column space of a matrix. Means you take all the columns of a matrix and take all possible linear combinations that you can make of the columns. Basically, you generate a set of vectors from the columns by doing this all possible linear combination, and that new space is called the span of the column, span of the vectors forming the column or the column space. So, that is what we are going to look at. So, look at the example which I have taken from the Strang's book 2020 book, which is called Linear Algebra for Everyone, but this is for reading Strang may not always be a very simple experience. Reading Strang you have to sometimes go and see other books, you sometimes have to go to his lecture, sometimes you have to take a careful look and think over it. But if you look at it carefully through his books, you will find a lot of gems there, and you learn the subject like never before. So, that is why I like Strang. Strang not because there is no other book which can be written or it cannot be written in a much better way, but Strang leaves loose ends. Strang gives you some very good insight by which you can catch up and bind up those loose ends and get a fantastic view of the subject, and that helps for anyone else who is like me, who is using many other works in linear algebra to teach this course, apart along with keeping the Strang's one as the main one, actually can write up something much interesting for the students and much clear. So, let us take Strang's thing. So, if you look at these three vectors, none of the vectors here cannot be expressed as a linear combination of the other two. For example, V3 which is 006 cannot be expressed as alpha V1 plus beta V2. You cannot find any alpha and beta which will show that the sum make alpha of V1 plus beta of V2 equal to V3, where V1, V2, V3 are these vectors. So, okay, assume that there is some alpha beta, suppose that I can do that, then I must have this vector equation. Now, then I look at it component wise. If I look at it component wise, here I will multiply by alpha, alpha, 2 alpha, 3 alpha, here it will beta into 0, 0, 4 beta, 5 beta. So, then I add these two vectors, I will have alpha, 2 alpha plus 0, alpha plus 4 beta, 3 alpha plus 5 beta, and this vector is same as 006. So, alpha must be 0 and beta must become also 4 alpha plus 2 alpha plus 4 beta is also 0. So, you will get beta is equal to 0 once you put alpha equal to 0, because this will become 0, 4 beta equal to 0. So, beta is equal to 0. Now, you have alpha and beta equal to 0. Now, we have 3 alpha plus 5 beta equal to 6. If you put alpha and beta equal to 0, you have 0 equal to 6, which is a contradiction. So, you cannot find any numbers alpha beta which solve this system of 3 equations in 2 variables. So, what does it tell you? It tells you if you have more equations and less number of variables, the system in general does not have a solution. This is a key thing. So, which means these vectors are somehow independent of each other, and such vectors are called linearly independent vectors. Each of them in space is providing a different direction. So, you can check it for the others. Others also do not have. Suppose you want to make V2 as a linear combination of V3 and V1, you will again fail. Now, take any vector. Now, these are 3 independent directions. Now, let us look at that. If I take these 3 vectors now, this V1, V2, V3, which is 1, 2, 3, 0, 4, 5 and 0, 0, 6 from the matrix, then I want to tell you that if I take any vector in R3, does not matter what is the vector, I can very simply show that corresponding to each such vector B equal to B1, B2, B3 in R3, there are alpha, beta, gamma which solves this system of equations. So, here I have 3 equations in 3 unknowns. So, it is a system where the number of unknowns equal the number of A, and here corresponding to every B there will be a unique alpha, beta and gamma which solves this equation. So, in that sense we say that these 3 vectors span the whole R3, and these are called the basis vectors of R3, one of the set of basis vectors of R3. Let us look at the calculation. If you look at this, I will have beta 1 equal to B1 equal to alpha, beta 2 equal to 2 alpha plus beta, and immediately you will from here alpha is equal to beta 1 and beta 2 is equal to 2 beta plus beta 1 2. So, B2 minus 2 B1 is beta, right. Okay. So, and B3 you can again compute out by putting the values of B3 is 3 alpha plus 5, 3 alpha plus 5 beta plus 6 gamma. So, once you know alpha and once you know beta, you can then compute out what is B3, which is this in terms of B3, and hence you can from B3 is given, B1, B2, B3 are given. So, once you have computed out alpha in terms of B1, beta in terms of B2 and B1, you can calculate out gamma in terms of B1, B2 and B3. So, since B1, B2, B3 are given, so for that particular B1, B2, B3, I have uniquely determined alpha, beta and gamma in terms of B1, B2, B3 for these set of so called linearly independent vectors. So, which means I can express any vector in R3 uniquely as a linear combination of those 3 vectors, means the linear combination scalars alpha, beta, gamma are unique to this vector. You change the vector V, the alpha, beta, gamma will change. In the linear algebra language, we say that R3 is spanned by the vectors beta 1, beta 2, where V1, V2, V3 and the set V1, V2, V3 is called a basis of R3. That is, if I know these 3 vectors, I can know R3. So, if I know these 3 vectors, I can know about R3, and whatever I can want, once I know anything about these 3 vectors, I know about R3. So, this whole infinite, a space with infinite, uncountably infinite points R3 or uncountably infinite vectors, that story can be told, story of such essentially a very complex stuff can be told in using just 3 vectors, and this is the whole drama, whole central point of linear algebra, and also at the same time observe that the central technique, the central fundamental feature is linear combination of vectors with scalars. Linear combination remains to be the guiding principle of linear algebra. So, what does it say? So, if B equal to beta 1, V1, V2, Vn be a given basis in Rn. So, in Rn the number of elements of the basis must exactly be in n. Those things we will come in the later class, in the possibly next week, not this week. But one thing is clear, that if you have such, say in R3 of those 3 independent vectors, then for every V in Rn we will have unique real numbers, because these real numbers that we have got alpha, beta, gamma is unique for a given V. For every given V, we will have unique real numbers depending on the choice that V you make. You will have V equal to alpha 1 beta V1 plus dot dot alpha and Vn. So, under the basis V1, V2, Vn, alpha 1, alpha 2 and alpha n are called the coordinates of the vector V, and that is exactly what I have written. So, under the basis V, V can be given a coordinate representation, and these coordinate representations are those unique vectors whose linear those unique scalars whose linear combinations with vectors v1, v2, vn produces the vector v. That those scalars are the coordinates of the vector v in that basis. So, let us look at the things in R3. Consider the identity matrix. Then we have already learned what is multiplication of a vector matrix with a vector. So, here I x would return me x. So, it is identity. So, it will not change any position. So, of any position of x1, x2, x3. So, I x is x. So, x1, x2, x3 is equal to x1 into 1 0 0 plus x2 into 0 1 0 into 0 0 1. So, and hence automatically x1, x2, x3 are the coordinates, which is clear to us, which we understand. So, these are called the natural basis or the canonical basis of R3. Now, let us give a formal definition of linear independence in it should be Rn. I have written R3 by mistake. When you keep on writing pretty fast, there is a huge chance of you making a mistake, and which I seem to be doing pretty often. And so, I beg forgiveness from my viewers from the beginning, and the viewers, my students and any other viewer can actually point this out to me, and I would be very, very happy. So, a set of vectors v1, v2, vk are called linearly independent if for scalars alpha 1, alpha 2, alpha k, whenever I have this expression alpha 1 v1 plus alpha 2 v2 plus alpha k v equal to 0, this all must reduce to 0, just as this had reduced to 0 basically. Here these are actually linearly independent vectors, but why didn't it give unique alpha beta for 0 0 6? Because I needed another linearly independent vector with it to give me the unique values of alpha, beta and gamma, right. So, these two do not generate the whole space R3. So, for generating R3 I need 3 linearly independent vectors, but these two themselves are linearly independent. So, linear independence actually means this, that none of the vectors can be written as a linear combination of the others. If one of the vectors can be written as a linear combination of the others, you immediately get linear dependence. See what happens if any one of these vectors v1, v2, vk is a 0 vector, then that set of vectors cannot be linearly independent, because I can always take the alpha that I have in front of 0 can be anything, because alpha into 0 would give me 0, and I can put the rest of the alpha 1 alpha k to be 0. Say the second element v2 was 0. So, I will put alpha 2 equal to say 20 and rest are 0. So, but this equation will be satisfied. Basically, I can write alpha into 20 or minus 20 into alpha is equal to alpha 1 v 1 plus alpha 3 v 3 plus dot dot alpha k v q. So, I have expressed the vector 0, because I can now divide all the sides by 20 as a linear combination of v 1 v 3 dot 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 v 2. I am expressing the vector v 2 basically as a linear combination of the rest of the vectors v 1, v 3, v 4 to v k. So, if you can't express any one of them as a linear combination of any other set of other vectors, the set of the remaining vectors, then this condition must hold, and that is called linear independence. Spanning set of a vector is that you take some vectors and make all possible linear combination. The set of all linear combination of a given set of vectors is called the spanning set of the vector v, or the span of v, right. So, this is not a very big issue. So, you take the vectors v 1, v 2, v k, and then you take all possible, you keep on changing these alpha i's, then all possible linear combinations will be generated and you will have a new space and that will be called new vector space, will be called the span of V. Just V as V1, V2, Vk, this is just few things, they are not vector space. So, with just this finite number of things, we are generating this vector space. Some important fact is that the maximum number of linearly independent vectors in Rn is n, it cannot exceed that. A basis in Rn, n could be anything 2, 3, 4 whatever, contains exactly n linearly independent vectors whose span is Rn. This is a very fundamental thing. This is the key idea behind the fact that we say Rn is an n dimensional space. So, for a finite dimensional vector space, the number of elements is the basis actually equals its geometrical dimension, of which we have a very good intuition, and this is a very fundamental fact. So, essentially if you look at the definition of dimension, linear algebra books would say that okay, number of elements of a basis is the dimension, but no, we call n to be a dimension of a vector space V or vector space Rn, say if all the basis sets have exactly n linearly independent vectors. If I do not have a function, if I have some space where the dimension is not finite, I cannot geometrically get an intuition that its dimension is finite. If I have R3, you can immediately understand my dimension is finite, length, breadth, height. So, if you R4 in physics, length, breadth, height and time, right, 3 space variable, 1 time variable. So, it is in R4. So, that kind of thing. So, you will immediately understand that dimension is finite, you have the geometrical sense. So, your geometrical intuition has to be used, but there are certain spaces for which you will have no geometric sense that it could be finite, that this vector space has finite dimensions, and in that case you will find that there are various sets of linearly independent vectors who span the whole set, but their numbers are not fixed, that there are numbers only there. So, for every basis has only say 50 elements possible. So, with just 50 elements, 50 linearly elements, I am generating all every basis has only has 50 elements, then we say the dimension is 50. Every basis has 5 elements and the dimension is 5. So, this definition that the number of elements of a basis is a dimension is something still very tricky to me after so many years, because it is actually the geometric intuition of the dimension is known, and now you can say if I am in Rn, I can show that the number of basis vectors will always be exactly n. If I have n plus 1 elements in the basis, if I have n plus 1 linearly independent elements, if I have n plus 1 elements, they cannot be linearly independent. So, which means that cannot be the basis, because basis elements basis elements have to be linearly independent, and the number of maximum linearly independent vectors. So, you take a set of vectors, what is the maximum number of linearly independent elements it can have? It is n. If I have n plus 1 vectors, then the set of vectors is not linearly independent in Rn. So, any size of vectors on any set of vectors which is more than n cannot be linearly independent and cannot be a basis. So, of course, you can question that can there be a number of say k linearly independent vectors in Rn and that spans Rn? No, and k is strictly less than n. No, that will not happen. It can only span if k is equal to n. If k is strictly less than n, we can always show an element for which I am unable to find those alpha beta commas, right. So, that is the key idea. So, there I had only I had 2 vectors, not 3 vectors. For example, consider this vector, say consider the 3 dimensional space and consider V1 as 1 0 0 and 0 1 0. These vectors are also linearly independent, you can figure out. alpha plus beta, alpha of 1 1 0 plus beta of 0 1 0 equal to 0 means first will give you alpha equal to 0, the second line will give you beta equal to 0, right. So, it will immediately tell me these are linearly independent, but these vectors do not form the space R3. These vectors only span, if you add these two vectors and you take a linear combination, shrink, stretch, change direction, whatever you do, all the possible linear addition and linear combinations of these two vectors will lie in on the xy plane. So, the span of V1 would be xy plane and not the whole space. Even though those two vectors are linearly independent, the maximum number of linearly independent vectors in R3 is 3, here it is strictly less, and so this cannot span R3. So, but if you take this alpha beta gamma which is linearly independent, then of course, you will immediately realize that this will span R3. Let us see how it spans R3. So, if I take any x1, x2, x3 in R3, then I have to find alpha, beta, gamma. You see, observe, this is not the canonical basis. Here I have not, I do not have 0 0 1, but 1 1 1. In R2, for example, any two vectors whose angle between them is not 0 or 180. If it is 0 or 180, there 0 means it is in the same line, in the same direction. So, which means one of them is some alpha times the other. They must be in the same directions on the same line. So, they must be have been stretched or shrunk from one another, can be stretched or shrunk from one another. So, they are linearly dependent. Or if it is 180 means it is minus times something. So, that is also linearly dependent, some linear relationship. While if you have any two vectors in R2 which does not, the angle between them is not 0 or 180, cannot be linearly dependent, they have to be linearly independent. So, here I have chosen these two vectors and the vector here not 0 0 1, but one which makes 45 degree angle with this vectors, that even with the vector 0 0 1, the point the vector 1 1 1, that is the vector whose tip is the point 1 1 1. And now I try to see, though in the normal Cartesian coordinates, if x1 x2 x3 is the basic is the coordinates in the canonical basis which we are habituated with x1 x2 x3, then what are the coordinates in this basis which is not the canonical basis? Those coordinates, as I said, are these alpha beta gammas whose the unique alpha beta gammas whose linear combination actually builds up this x1 x2 x3. Here you can it shows that if I calculate here, x1 is alpha plus gamma, x2 is beta plus gamma, and x3 is gamma from these equations. So, what do I get? Alpha is equal to x1 minus x3 because x1 minus gamma is alpha, beta is x2 minus x3 and gamma is x3. So, here once given x1, x2, x3, my alpha, beta, gamma are known. So, the vector x which is given by the coordinates x1, x2, x3 in the canonical basis under the basis v tilde, where 0 0 1 is replaced by 1 1 1, the coordinates are x1 minus x3, x2 minus x3 and x3. So, change of basis, you change everything, the coordinates changes. So, as the basis changes, so does the coordinates. So, let us look at some other aspects like linear dependence now. So, consider this vector 1 1 1 2 2 2 0 1 0. So, 2 2 2 is obviously linear combination of these two, because 2 2 2 is 2 of 1 1 1 plus 0 of course, this is no longer required. So, 0 into 1 0 1. So, one of the three vectors can be expressed as a linear combination of the other two, which means these three are not linearly independent. So, you take B1, B2, B3 in R3 and see whether three vectors oh, and they are not linearly independent, can they span R3? Let us check the calculation. If you try it with yourself, beta 1 would be alpha plus 2 beta plus gamma, beta 2 would be alpha plus 2 beta plus 0, B3 would be alpha plus 2 beta plus gamma. So, what do we have? What do I have? From here, I am able to prove that gamma is equal to gamma could be B1 minus B2 and gamma could be also B3 minus B2. So, basically here gamma is not unique to give me B1, B2, B3, right, because gamma is not unique, because what happens here, beta 1 plus alpha plus 2 beta plus gamma. So, here beta 1 is equal to beta 2 is alpha plus 2 beta. So, this is nothing but beta 2 plus gamma, this is B3 is nothing but beta 2 plus gamma, beta 1 is nothing but beta 2 plus gamma. So, gamma is not unique. So, which means this alpha beta need not be unique either. So, here if I take these three elements, then for the given B1, B2, B3, I need this alpha beta gamma may solve the system, there will be a solution, but that need not be unique. You keep this in mind because these three vectors can be collected into a matrix, and I can write this as that matrix times the vector alpha beta gamma is equal to B1, B2, B3. What are alpha beta gamma? What I see here is that if these column vectors are not linearly independent, this alpha beta gamma need not be unique, and this is the key idea to solve system of linear equations, which you have learnt at school with two variables possibly, maybe, but what happens if there are hugely large number of variables, which is exactly what happens in many subjects in practice, and then what is the key idea to solve it. So, that is the idea that if I do not have linearly independence, this can have more than one solution, maybe have infinite solutions possible. Okay, that is the key idea. So, linear dependence, what does it mean? So, linear dependence means if you have a set of vectors, one of the vectors can be expressed as a linear combination of the others, which can be now summed up and put in to this framework, that if there are scalars alpha 1, alpha 2, alpha k and the vectors beta 1, beta 2, beta k, such that alpha 1 V 1 plus alpha 2 V 2 plus alpha k V k equal to 0, and at least one of them is one of the alpha 1, alpha 2, alpha k is not equal to 0, then we call V 1, V 2, V k to be linearly dependent. Suppose alpha 1 is not equal to 0, then I can write alpha 1 V 1 is equal to minus alpha 2 V 2 minus alpha 3 V 3 minus alpha k V k, right. And then because alpha 1 is not 0, I can divide both sides to write V 1 equal to minus alpha 2 V 2 minus alpha 2 by alpha 1 V 2 minus alpha 3 by alpha 1 V 3 dot minus alpha k by alpha 1 V k. So, I have written V 1 as a linear combination of the rest. So, they cannot be linearly independent. Basically, any vector V whose coefficient is 0, non-zero, can be expressed as a linear combination of the rest, and that is the key idea. So, they cannot be independent of each other, they are dependent, linked through these linear combinations. So, now we give the definition of, after so much talk, we give the definition of the column space of A. So, you take any vector x in Rn and form the product A of x, where A is a matrix with certain columns. So, basically what you take take the linear combination of all possible linear combinations of the columns of A, and or basically linear span of the column vectors of A, and that would be called the column space of A or CA. For example, if you take I is 0 0 0 1 0 0 0 1, you will immediately have the column space of I is R3, but you have a matrix like this where one of the column vectors is 0. If one of the column vectors is 0, you can understand all the three column vectors are not linearly independent. So, these are three elements which are not linearly independent. Then only two elements, that is 1 0 0 and 0 1 0, these are linearly independent, and the third one, if I club the third one, is not linearly independent. So, they cannot be a basis of R3, and hence C of A can only generate R2, because 1 0 0 0 1 0 are linearly independent vectors and they are lying on the xy plane. So, here the column space of A is R2, the xy plane. These cannot form a basis of R3. So, all the possible linear combinations do not generate R3, because R3, to generate R3, the set of the basis set must have exactly 3 linearly independent elements. Once you have a 0 vector among them, as I told you, the set of vectors cannot be linearly independent. Okay, here I have written, okay, if 0 0 is present among the set of vectors, show that y it is linearly dependent. Basically, these set of vectors will never be 0. For example, I have x, this is very simple. If you take x y z, just think x y z equal to alpha of 1 0 0 plus beta of 0 1 0 plus gamma of 0 0 0. So, you will have, you will have x is equal to alpha, y is equal to beta, but gamma would be what? Gamma would be 0. So, they are generating elements of the form x y alpha beta 0. What is that? Those are all lying in the xy plane. So, they are generating a space, but that is not R3. So, their span of these three vectors is R2 or the xy plane embedded in R3. So, the number of linearly independent columns of a matrix is also called the rank of a matrix, right. So, that is important idea, and rank obviously has to be the minimum of m and n, because what we can show that if I take the row vectors, the number of row vectors which are linearly independent would be exactly equal to the number of column vectors which are linearly independent, and that is the key idea. So, that would lead us to focus on something called rank 1 matrix. Right here is this whole story of rank 1 matrices. Just let me. So, if I have n linearly independent columns, I cannot have more than n linearly independent rows, then I will have n linearly independent rows also. So, if m and n, suppose m is bigger than n, then, and if n is the number of linearly independent columns, so m must be strictly bigger than n. Those, or if the number of columns is bigger and m is smaller, then the rank of a maximum can be m, it cannot exceed. So, the rank of A is, the maximum rank would be the minimum of m and n. Of course, it could be less, right, depending on the as less number of linearly independent vectors you have. So, let us get an insight into what has just been discussed, and we follow on the matrices of rank 1. So, let us look at this matrix of rank 1, so called. Why it I call rank 1? So, there is only one linearly independent vector, because take the columns C1, C2, C3. You take any two of them, they are not linearly independent, they are dependent, any two of them, C1, C3, C1, C2, C2, C3. So, no two vectors here is linearly independent. So, the rank cannot be 2, no question of rank being 3, the rank cannot be 2, right, because if I write here C2 is equal to 3 C1, I can write C2 equal to 3 C1 plus 0 C3. So, every vector is expressed as a linear combination of the other two, because the other that is missing here can be added up with a 0, right. So, every vector, every C1 or C2 or C3, everything can be expressed as the sum of the other two. So, they are not linearly independent, and as a result of which, so their rank cannot be 3. So, there is not 3 linearly independent vectors. So, let me forget those things, let me just throw off the things, 3 ko forget karo. So, now I think can the rank be 2? Now, take any 2 of them, but no, see those no 2 of them are linearly independent. So, the rank has to be 1, and it has to be 1 because so the only possible that these vectors are non-zero, any non-zero vector is a linearly independent vector, and that is it. So, what about the rows here? So, the rows also have a relation amongst each other, the rows also are linearly dependent, right. So these are called intuitive, these are called matrices of rank 1, and they are very important. A lot of matrices can be decomposed into matrices of rank 1. So, one of the most important thing that we learned from matrices of rank 1 by looking at them is that row rank must be equal to column rank. I have already mentioned that the number of linear independent rows and the number of linear independent columns must be same, but from rank 1 matrix we have essentially shown through this example that the number of linearly independent columns and the number of linearly independent rows are same, and the number of independent rows of a matrix is called the row rank of A. In fact, the row rank of A is equal to the rank of A is equal to the column rank of A. So, the normal rank is called the column rank of A. So, this result that the number of linear independent rows must equal the number of linear independent columns is what is called the first grade theorem of linear algebra by Gilbert-Stein, and it is absolutely fascinating, and it is very spine chilling, but it is very fantastic. When I first thought of that deeply, not in my undergraduate days, after that, isn't that fascinating that the number of linearly independent columns must exactly be equal to the number of independent rows. I think this is a marvelous fact. The rest part I am not discussing here, so people can see from the notes. Those students who would be there and those who are viewers, you need not get worried, and there is some story about complex matrices. This is a detour, and this detour will not be discussed in this discussion. Students can see it. If there is a question, they can ask me. So, with this I end my discussion here, and I thank all of you for the attendance, very long classes. Thank you very much.